April 1945. The skies above Okinawa. Lieutenant Commander Minoru Genda stood in the technical hangar at Kanoya Air Base, staring at what should have been impossible. Before him sat an F4U Corsair, nearly intact, its distinctive inverted gull wings still attached, its massive cowling housing an engine that had become legend among Japanese pilots. The aircraft had been recovered 3 days earlier from shallow water off the southern coast, after its pilot ditched following what appeared to be fuel system failure. Standard procedure called for documenting the wreckage and extracting useful intelligence. But Genda, one of Japan's most experienced test pilots, and the man who had helped plan the Pearl Harbor attack, had different intentions. He wanted to fly it. To understand from the pilot's seat why this American fighter had become the most feared aircraft in the Pacific. Why Japanese pilots radioed warnings when Corsairs appeared. Why even experienced aces in the newest Japanese fighters avoided engagement when possible. The answer, he suspected, lay in the massive Pratt Whitney R-2800 engine. 2,000 horsepower, nearly double what Japan's most powerful fighters could produce. But numbers on paper told incomplete stories. Genda needed to feel that power, to experience what American pilots experienced every time they advanced their throttles. Only then would he truly understand how far Japan had fallen behind. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The path to this moment had begun 4 years earlier, when Japan still believed victory was achievable. In December 1941, Japanese naval aviation was arguably the world's finest. The Mitsubishi A-6M0 fighter outperformed every opponent it encountered. Japanese pilots were superbly trained, many with combat experience from China. Japanese aircraft carriers were the most capable, afloat. The surprise attack on Pearl Harbor demonstrated operational excellence that shocked the world. But American industrial capacity was already mobilizing. Factories were converting from civilian to military production. Aircraft manufacturers were scaling up operations. Engine designers were pushing boundaries of what radial and inline engines could achieve. The Americans understood something Japan's leadership failed to grasp. Modern war was industrial war. Victory would go not to the nation with the best pilots or the most elegant designs, but to the nation that could produce overwhelming quantities of adequate equipment and continually improve that equipment faster than enemies could respond. The F4U Corsair's development began in February 1938, when the United States Navy's Bureau of Aeronautics issued specification requesting a single-seat carrier fighter capable of maximum speed. The Navy wanted 400 miles per hour, extraordinary performance for that era when most fighters struggled to reach 350. They wanted heavy armament, long range, and the ability to operate from carrier decks. It was an ambitious list of requirements that would force radical solutions. Chance Vought Aircraft's chief designer, Rex Beisel, examined the specifications and made a bold decision. Rather than compromise on any requirement, he would build the smallest practical airframe around the largest, most powerful engine available. That engine was the Pratt Whitney R-2800 Double Wasp, an 18-cylinder, 2-row radial producing 2,000 horsepower. No fighter had ever been designed around such a powerful engine. The challenges were immediate and substantial. To harness 2,000 horsepower required a massive propeller. Beisel's team designed a 13-foot, 4-inch diameter propeller, the largest ever fitted to a fighter aircraft. But such a large propeller created problems. How could they provide adequate ground clearance while, say, maintaining the structural efficiency needed for carrier operations? The solution became the Corsair's most distinctive feature. Instead of conventional straight wings, Beisel created an inverted gull wing design. The wings angled downward from the fuselage before leveling out, creating a distinctive M shape when viewed from front. This configuration allowed relatively short landing gear while providing propeller clearance. The design also created optimal aerodynamic conditions where the wing met the fuselage, minimizing drag. The prototype XF4U-1 first flew on May 29, 1940. On October 1, 1940, test pilot Lyman Bullard achieved 405 miles per hour during a speed run between Stratford and Hartford, Connecticut, with tailwind assistance. Headlines proclaimed it the first American single-engine fighter to reach 400 miles per hour. The aircraft's actual maximum level flight speed was 378 miles per hour at 23,500 feet, still exceptional performance. Production F4U Corsairs began reaching operational units in late 1942. Marine Fighter Squadron VMF 124 received the first combat-ready aircraft, deploying to Henderson Field on Guadalcanal in February 1943. Japanese pilots had been receiving reports of a new American fighter. Intelligence described it as large, fast, and heavily armed. But reports could not convey what facing a Corsair actually meant. The Corsair's combat debut proved inauspicious. On February 14, 1943, during what became known as the St. Valentine's Day Massacre, American forces suffered devastating losses. 9 American aircraft were shot down, including Corsairs, P-38 Lightnings, P-40 Warhawks, and bombers. Japanese defenders lost only a single 0. The 9-to-1 loss ratio in Japan's favor was so severe that daylight bombing missions were suspended pending tactical reassessment. This engagement demonstrated that superior technology alone could not guarantee victory. But American pilots adapted quickly. They learned the Corsair's strengths lay not in dogfighting but in what became known as boom and zoom tactics. The Corsair could not outturn a 0 in slow-speed maneuvering. Japanese fighters retained advantages in low-speed handling and instantaneous turn rates. But the Corsair could outdive, outclimb, and outrun any Japanese fighter. Proper tactics meant maintaining speed and altitude advantage, diving on enemy aircraft, firing, and using superior speed to disengage before the enemy could respond. Second Lieutenant Kenneth Walsh of VMF 124 mastered these tactics, becoming the first Corsair ace on May 13, 1943. He would eventually achieve 21 victories, demonstrating what the aircraft could accomplish in skilled hands. As 1943 progressed into 1944, the Corsair's reputation grew. Marine squadrons, flying from hastily constructed coral airstrips, exploited the aircraft's ruggedness. The Corsair proved capable of absorbing battle damage that would have destroyed lighter Japanese fighters. Its 650 caliber Browning machine guns provided overwhelming firepower. The 4 inboard guns carried 400 rounds each. The 2 outboard guns carried 375 rounds each, totaling 2,350 rounds of ammunition. Later variants replaced the machine guns with 4 20mm cannons, though many pilots preferred the reliability and ammunition capacity of the 50 caliber weapons. Japanese pilots who survived encounters with Corsairs reported consistent observations. The American fighter was fast, faster than anything Japan produced. It could dive away from any pursuit. It could climb rapidly to altitude advantage. Its firepower was devastating. A single burst from 650 caliber machine guns could shred a 0's lightly built structure. Most troubling was the Corsair's apparent indestructibility. Japanese pilots scored hits that should have been fatal, watching their cannon shells strike the American fighter, but the Corsair absorbed the damage and kept fighting. Squadron reports documented these encounters. Engaged enemy Corsairs at 15,000 feet. Our pilots achieved multiple hits, but enemy aircraft did not fall. Enemy used superior speed to disengage when damaged. Our lighter aircraft cannot pursue. Another report noted. Corsair fighters attacked our formation from high altitude. They dove through our formation firing, then climbed away before our fighters could respond. We cannot match their rate of climb or diving speed. By mid-1944, Japanese pilots understood they were facing technological superiority they could not overcome through skill alone. The psychological impact was corrosive. Young pilots, fresh from abbreviated training programs, faced American fighters that outperformed their own aircraft in nearly every category. Even experienced pilots found themselves unable to press advantages because Corsairs could simply accelerate away from danger. The Corsair's versatility extended beyond air combat. By mid-1944, Corsairs regularly carried external ordnance, 1,000-pound bombs on centerline and wing racks, 8 5-inch high-velocity aircraft rockets, napalm canisters. This fighter-bomber capability made the Corsair invaluable for close air support during amphibious operations. During the Okinawa campaign in 1945, Corsairs flew thousands of ground attack sorties, earning the nickname Angels of Okinawa from grateful infantrymen. But what truly separated the Corsair from Japanese fighters was the engine. The Pratt Whitney R-2800 Double Wasp represented American aero engine development at its peak. 18 cylinders arranged in 2 rows of 9, displacing 2,800 cubic inches. At rated power, it produced 2,000 horsepower at 2,700 RPM. With water injection for emergency boost, it could briefly achieve 2,250 horsepower. Japanese engine development had followed different paths. The Nakajima-Sake radial engine that powered the Zero displaced 1,000 cubic inches and produced 1,130 horsepower. Japan's most powerful production fighter engine, the Nakajima Homare radial, displaced 1,990 cubic inches and was rated at 1,800 horsepower. But the Homare suffered chronic reliability problems. Overheating, bearing failures, and inconsistent power output plagued the engine throughout its service life. The gap was not just in raw horsepower. American engines consistently delivered their rated power for hundreds of hours between overhauls. Japanese engines, even new examples, often failed to achieve their theoretical power ratings and required frequent maintenance. The difference came from metallurgy, manufacturing precision, better lubricants, and more sophisticated quality control. American industry could produce engine components to tolerances measured in thousandths of an inch, with consistent quality across thousands of engines. Japanese manufacturing struggled to achieve such precision, particularly as the war progressed and skilled workers became scarce. Lieutenant Commander Genda understood these disparities intellectually. He had read technical reports on captured American equipment. He had debriefed pilots who faced Corsairs in combat. He had studied intelligence assessments of American manufacturing capacity, but intellectual understanding was incomplete. He needed experiential knowledge. He needed to sit in the cockpit, start that massive engine, feel 2,000 horsepower respond to his throttle inputs. Only then would he fully grasp what Japanese pilots faced every time Corsairs appeared. The captured Corsair had been partially disassembled for technical examination. Engineers from the Yokosuka Naval Air Technical Arsenal had documented every system, measured every component, analyzed manufacturing techniques. Their reports made sobering reading. In nearly every category examined, American technology exceeded Japanese capabilities. The gap represented years of industrial development, massive investments in research and tooling, sophisticated supply chains, and resources Japan simply did not possess. But Genda wanted more than technical reports. He wanted the aircraft made airworthy. It took 3 weeks of intensive work. The engine had suffered saltwater contamination during the ditching. Every cylinder had to be removed, cleaned, and inspected. Corroded components were replaced with parts scavenged from other wrecked Corsairs. The fuel system was flushed and tested. Control surfaces were examined for saltwater damage and repaired where necessary. The propeller mechanism required complete overhaul. Japanese mechanics approached the work with professional respect. They were working on an enemy aircraft, but they were also working on a masterpiece of engineering. Every system they examined revealed sophistication and quality that Japanese manufacturing could not match. The engine's construction was particularly impressive. Cylinders were precisely machined. Pistons, connecting rods, and crankshaft components showed surface finishes and dimensional accuracy that Japanese engine manufacturers struggled to achieve. The 2-stage supercharger system, designed to maintain power at high altitudes, incorporated complex internal passages and precisely fitted rotating components. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By late April 1945, the Corsair was ready. Genda conducted ground runs first, familiarizing himself with the cockpit layout and systems. The instrument panel was comprehensive, more gauges and controls than any Japanese fighter. Engine instruments, flight instruments, weapons systems, radio equipment, all clearly labeled and logically arranged. The cockpit felt substantial, well designed for long missions and combat operations. The control stick was heavier than Japanese fighters, requiring more force to move. The rudder pedals were widely spaced. Everything about the cockpit conveyed solidity and power. This was not a delicate machine requiring careful handling. This was a robust combat aircraft designed to absorb abuse and keep fighting. Genda advanced the throttle during ground testing. The engine's response was immediate and smooth. Power built progressively as RPM increased. At full throttle, the sound was overwhelming. 18 cylinders firing in rapid succession, producing vibration that shook the entire aircraft. The propeller's massive diameter created tremendous thrust, even at zero airspeed. Genda could feel the aircraft straining against the brakes, eager to move. He reduced throttle and considered what he was about to experience. This engine produced nearly twice the power of the Mitsubishi Kinsei Radial in his familiar A6M0. How would that power translate to flight characteristics? How would the aircraft handle? What would 2,000 horsepower feel like in combat maneuvers? On April 28, 1945, conditions were favorable. Clear skies, light winds, adequate runway length. Genda completed his pre-flight inspection personally, checking every surface, every control, every system. Japanese ground crew stood at safe distance, watching their commander prepare to fly an enemy aircraft. Some felt pride that Japanese technical skill had made this possible. Others felt unease at what this flight would confirm about Japan's technological inferiority. Genda climbed into the cockpit and strapped in. The seat was comfortable, well padded, adjustable for pilot size. The shoulder harness was substantial, designed to protect during violent maneuvers or crash landings. He worked through the starting procedure, following captured technical manuals that Japanese translators had prepared. Battery switches on, fuel selector to main tanks, mixture control to rich, propeller control to full increase RPM. Throttle cracked open slightly. He pressed the starter button. The engine turned over slowly at first, then caught. One cylinder fired, then another. Within seconds, all 18 cylinders were running. Blue smoke poured from the exhaust stacks as oil residue burned off. The engine settled into rough idle, vibrating the airframe. Genda advanced throttle slightly. The engine smoothed out, finding its rhythm. He checked instruments. Oil pressure rising to normal range, cylinder head temperatures climbing, engine RPM stable. Everything appeared normal. He released brakes and added power. The Corsair began rolling, slowly at first, then with increasing momentum, as he added more throttle. The tail came up quickly. Visibility over the long nose improved. He had been briefed that forward visibility on the ground was poor due to the nose's length and the cockpit's position. Taxiing required S-turns to see ahead, swinging the nose left and right to check for obstacles. At the runway threshold, he stopped and performed his final checks. Controls free and correct. Trim tabs set for takeoff. Flaps down 15 degrees. Fuel mixture rich. Propeller full forward. Cowl flaps open for cooling. Everything ready. He aligned with the runway center line and paused. This was the moment. Once he advanced that throttle and committed to takeoff, he would experience what American pilots experienced dozens of times daily. He would understand the Corsair's power from personal experience rather than second-hand reports. Genda advanced the throttle smoothly. The engine's response was instantaneous. Power surged. The Corsair leaped forward with acceleration that stunned him. In a zero, takeoff required gradual power application and careful handling as speed built. The Corsair simply surged ahead with overwhelming force. He corrected right rudder to counter torque. The rudder forces were heavy but manageable. Airspeed built rapidly. 40 knots, 50 knots, 60 knots. The tail lifted. Forward visibility improved dramatically. 70 knots, 80 knots. He eased back on the stick. The Corsair lifted off smoothly at 90 knots, far faster than a Zero's typical 60-knot takeoff speed. but the acceleration continued. 100 knots, 110. He raised the landing gear. The gear retracted smoothly into the wings. He reduced power slightly and trimmed for climb. The rate of climb astounded him. The vertical speed indicator showed 3,000 feet per minute initial climb rate. A Zero climbed at perhaps 2,000 feet per minute when new and lightly loaded. This American fighter was climbing 50% faster while carrying 6 heavy machine guns, armor protection, and full fuel. The climb felt effortless. The engine simply pulled the aircraft upward with power to spare. Genda leveled at 8,000 feet and began exploring the aircraft's handling. He started with gentle turns, feeling how the controls responded. The ailerons were heavier than he expected, requiring significant force for rapid rolls. But once rolled, the aircraft felt stable and predictable. He tried a harder turn, pulling back on the stick to load the aircraft. The Corsair responded smoothly, entering a 60-degree bank turn. He maintained back pressure. The turn tightened. Airspeed bled off as lift was redirected from supporting weight to changing direction. Warning buffet began as the aircraft approached stall. He relaxed back pressure and rolled level. The aircraft recovered instantly. There was no tendency to snap or spin. The stall characteristics were benign, predictable. He climbed back to altitude and decided to test what he'd read in intelligence reports. The Corsair's diving speed was supposedly exceptional. Japanese pilots reported that Corsairs could dive away from any pursuit, accelerating to speeds where Japanese fighters encountered control problems or structural limits. Genda rolled inverted and pulled through into a steep dive. The nose dropped toward the ocean below. He advanced throttle to full power and let the aircraft accelerate. The acceleration in the dive was extraordinary. Airspeed built rapidly. 250 knots, 300 knots, 350 knots. The controls stiffened as dynamic pressure increased, but remained responsive. The airframe felt solid, no vibration, no buffeting, no sense of approaching structural limits. At 400 knots, faster than he had ever flown, Genda began recovery. He pulled back smoothly on the stick. The G-forces built as the aircraft's trajectory curved from downward to level. 4 Gs, 5 Gs. The G-suit he wasn't wearing would have helped, but he maintained consciousness through muscle-tensing techniques. The Corsair pulled out of the dive smoothly, climbing on momentum alone back above 6,000 feet. The entire maneuver had demonstrated something profound. This aircraft could dive to speeds no Japanese fighter could match and recover without structural damage. Any pursuit was hopeless once a Corsair decided to disengage. Genda climbed back to 10,000 feet and considered what combat maneuvers would reveal. He rolled into a maximum performance turn, pulling hard back pressure to simulate combat maneuvering. The aircraft turned tightly, but not as tightly as a Zero. The Corsair's higher wing loading, its weight distributed over smaller wing area, meant it could not match the Zero's instantaneous turn rate. But something else became apparent. The turn felt sustainable. The engine's massive power meant energy loss was minimal. In a Zero, hard maneuvering quickly depleted airspeed. Pilots learned to manage their energy carefully because recovering lost speed required time. The Corsair seemed to maintain energy effortlessly. He tried a series of hard reversals, rolling from one direction to the other in simulated scissors maneuvers. The heavy ailerons required significant strength, but the aircraft responded predictably. What struck him was the ability to maintain speed throughout. The engine simply overpowered the drag from hard maneuvering. This was the key insight. Japanese fighters outturned American fighters in single instances. But combat was not single turns. It was sustained maneuvering where energy management determined survival. The Corsair's power advantage meant it could sustain maneuvers that would bleed a Zero's energy to nothing. Genda performed a series of vertical maneuvers. Loops, Immelmanns, split-S reversals. In every case, the Corsair maintained speed and energy. The engine's power was simply overwhelming. He could point the nose upward at angles. That would stall a Zero, and the Corsair simply climbed, defying gravity through raw power. The two-stage supercharger maintained power even as altitude increased. At 15,000 feet, the engine still produced nearly full-rated horsepower. Japanese engines lost power significantly at altitude. The Nakajima Sakai that powered the Zero was optimized for low to medium altitude performance. Above 15,000 feet, power dropped noticeably. He climbed to 20,000 feet. The supercharger's second stage engaged automatically, maintaining manifold pressure. The engine continued producing power that seemed limitless. At 25,000 feet, higher than most combat occurred, the Corsair still had performance margins. He could maneuver, accelerate, climb. A Zero at this altitude would be struggling, its engine gasping for air, its performance degraded to the point where it became vulnerable. The implications were devastating. American pilots could choose their engagement, altitude. They could fight where their aircraft performed best, and Japanese fighters struggled. If Japanese pilots tried to climb to contest altitude advantage, Corsairs simply outclimbed them. If Japanese pilots remained at lower altitude, Corsairs dove from above with speed and energy advantages that made defense nearly impossible. Genda descended back to 5,000 feet and considered the weapons systems. He had no live ammunition, but he could test the gun charging mechanisms and simulate firing. The gun sight was sophisticated, a reflector sight that projected an illuminated reticle onto a glass panel. The reticle showed where bullets would impact at specific ranges. Japanese fighters used simpler ring and bead sights that required more pilot skill to use effectively. He pressed the charging buttons. Electric motors charged the guns, pulling the charging handles that would chamber rounds if ammunition were present. The system worked smoothly, requiring only button presses, rather than manual charging. He placed his thumb on the firing button and simulated firing. The button was well positioned, easily reachable, without looking. In combat, with adrenaline surging and targets fleeting, such ergonomics mattered enormously. He tried various firing positions, high deflection shots, low-angle approaches, head-on passes. In every case, the gun sight and firing controls felt natural and intuitive. The 650 caliber machine guns, though not firing, represented another massive advantage. Each gun fired approximately 800 rounds per minute. 6 guns together fired 4,800 rounds per minute, 80 rounds every second. The ammunition load of 2,350 rounds represented approximately 29 seconds of firing time if all guns were fired continuously. In combat, pilots fired in bursts of 1 to 2 seconds. The ammunition load represented dozens of firing opportunities. Japanese fighters typically carried much less ammunition. The Zero's two 20mm cannons carried 60 rounds each, approximately 7 seconds of firing time. The two 7.7mm machine guns carried 680 rounds each, approximately 53 seconds of firing. But the 7.7mm rounds were far less powerful than 50 caliber rounds. The Corsair's ammunition advantage meant American pilots could fire more often, with more powerful weapons, achieving more destructive effects per hit. Genda spent another 30 minutes exploring the aircraft's characteristics. He practiced carrier approach profiles, though he would land on the airfield rather than attempting an actual carrier landing. The approach speed was high, approximately 90 knots with flaps down, but the aircraft felt stable and controllable. Visibility over the nose during approach was poor, requiring careful judgment of altitude and distance. He understood why carrier landing in Corsairs had initially proved difficult for American pilots. The combination of high approach speed, poor forward visibility, and tendency to bounce if landing was not precise had led to numerous accidents. The Navy had initially deployed Corsairs primarily to land-based Marine squadrons, while continuing to use F-6F Hellcats on carriers. By mid-1944, improved pilot training and minor aircraft modifications had solved most carrier landing problems. Corsairs began operating routinely from carriers, providing fleet air defense and strike capabilities. But the learning curve had been steep, requiring dozens of pilots and aircraft lost to landing accidents before procedures were perfected. Genda turned toward Kanoya Air Base and prepared for landing. He reduced power and descended, extending landing gear and flaps. The aircraft's speed bled off. He turned onto final approach, aligning with the runway. The nose blocked his view of the runway completely. He flew the approach by reference to the runway edges, visible on either side, judging his height and distance. At 20 feet, he reduced power to idle. The Corsair settled. At 5 feet, he pulled back smoothly on the stick, raising the nose slightly. The main gear touched first, firmly but controllably. He held the stick back as speed decreased, keeping weight off the nose wheel. As speed dropped below 40 knots, the nose wheel settled onto the runway. He braked carefully, bringing the aircraft to walking speed, then taxied clear of the runway. He sat in the cockpit for a long moment after shutting down the engine. The sudden silence felt profound after the thunder of 18 cylinders. Ground crew approached, but he waved them back. He needed time to process what he had experienced. The flight had lasted 45 minutes. In that time, he had learned more about American technological superiority than months of reading reports could teach. The Corsair was not merely a good aircraft, it was a revolutionary machine that rendered Japanese fighters obsolete, not through any single advantage, but through the comprehensive superiority of its design and the massive power of its engine. That engine, the R2800, was the heart of everything. 2,000 horsepower enabled performance no Japanese fighter could match, diving speed that made escape impossible to prevent, climbing performance that seized and held altitude advantage, energy retention that sustained maneuvers until Japanese opponents ran out of speed and options. The engine represented American industrial capability, operating at levels Japan could not approach. Pratt Whitney had designed the R2000, 800 inches, the late 1930s. By 1945, they had produced over 50,000 examples, 50,000 engines, each precisely manufactured, each reliably producing its rated power, each capable of hundreds of hours of operation between overhauls. Japan's entire production of the Nakajima Homare engine, its most powerful radial, totaled approximately 32,000 units across all variants from 1941 through 1945, and those engines suffered chronic reliability problems that the R2800 did not. The production disparity told the real story. American industry could manufacture more engines, of higher quality, with better performance, while also producing everything else needed to wage global war: ships, tanks, trucks, artillery, ammunition, aircraft, electronics, all in quantities that overwhelmed opponents. Japan had mobilized its economy completely for total war. Civilian production had been stripped to bare minimums. Every factory that could be converted to military production had been converted. The population endured severe shortages of food, clothing, and necessities. Yet Japanese military production remained a fraction of American output. American factories produced military equipment while maintaining a civilian economy that provided its population with living standards citizens could only imagine. American soldiers ate better food than Japanese civilians. American logistics ensured troops in combat zones received hot meals, mail from home, medical care, and supplies that seemed limitless. Japanese soldiers often went hungry, received no mail for months, lacked basic medical supplies, and scrounged for ammunition and equipment. The captured Corsair represented this disparity in physical form. Every component, every system, every design choice reflected resources and capabilities Japan did not possess. The aluminum alloys in the airframe were superior metallurgy. The engine's precision manufacturing required machine tools Japan could not build. The instruments and systems reflected electronics knowledge where Japan lagged. The entire aircraft was evidence of American technological and industrial dominance. Genda climbed from the cockpit and walked around the Corsair. Ground crew waited respectfully at distance. He examined the aircraft from outside, seeing it with new understanding. The inverted gull wing was not merely distinctive styling. It was sophisticated engineering solving multiple problems simultaneously. The massive engine cowling housed a power plant that represented the apex of piston engine development. The 6 machine guns in the wings spoke to American understanding that overwhelming firepower won air combat. Everything about this aircraft was designed correctly for modern warfare's realities. Japanese aircraft design had followed different philosophy. Emphasis on maneuverability, lightweight, long range at expense of protection and firepower. In 1941, facing poorly equipped opponents, this philosophy had worked brilliantly. The Zero dominated early air combat in the Pacific, but as American technology and production improved, Japanese philosophy became liability. Lightweight meant vulnerability to battle damage. Emphasis on maneuverability sacrificed speed and climb rate. Long range came at expense of armor protection and self-sealing fuel tanks. By 1945, these choices had rendered Japanese fighters largely obsolete. Pilots in even the newest Japanese aircraft faced opponents with overwhelming advantages. The Kawanishi N-1K2J Shidenkai, Japan's best fighter at war's end, was an excellent aircraft. It could maneuver with American fighters. It had decent speed and climb rate. It carried heavy armament, but it arrived too late and in too few numbers. Total production of all N-1K variants was approximately 1,423 aircraft. The United States produced 12,571 Corsairs during the war. The production ratio, almost 9-to-1 in America's favor, meant that no matter how good the Shidenkai was, it could not affect the war's outcome. Japanese pilots flying superior aircraft still faced multiple American opponents in nearly every engagement. Outnumbered, short on fuel, lacking replacement parts, operating from damaged airfields under constant attack, they fought bravely but hopelessly. Genda returned to his office and began writing his report. He had been asked to assess the captured Corsair's capabilities and provide recommendations. His assessment would be honest. The Corsair represented comprehensive technological superiority in airframe design, engine performance, systems integration, and manufacturing quality. Japanese aviation could learn from examining this aircraft, but could not replicate its capabilities given current industrial limitations. Recommendations were more difficult. The war was clearly lost. American forces were closing on the home islands. The Navy had been destroyed at Leyte Gulf. The Army was collapsing in China and Southeast Asia. Air raids were systematically destroying Japanese cities. In this context, what recommendations could possibly matter? He wrote that Japanese aviation should study American design philosophy for future application. The emphasis on reliability, maintainability, and manufacturing efficiency represented lessons applicable beyond military aviation. American engineering focused on practical effectiveness rather than theoretical perfection. This approach served them well and should inform Japanese industrial rebuilding after the war. He paused at that phrase. After the war. Acknowledging defeat in an official document could be considered defeatist, perhaps even treasonous. But reality could not be denied. The war was ending. Japan had lost. The only questions remaining were how long the final agony would last and how much more destruction Japan would endure before accepting inevitable surrender. His report concluded with observations about the R-2800 engine specifically. This engine represented the culmination of years of development, massive investment in metallurgy and manufacturing infrastructure, and sophisticated quality control systems. Japan could not produce comparable engines given current industrial capabilities. Future engine development should emphasize reliability and manufacturability over maximum performance. Adequate engines produced in large quantities served better than sophisticated engines produced in limited numbers with questionable reliability. These were bitter lessons. They acknowledged Japanese inferiority in areas where national pride insisted on superiority. But Genda had spent his career in service of truth, not propaganda. His report would provide honest assessment regardless of how unwelcome that honesty might be. The report was filed with the Naval Air Technical Arsenal at Yokosuka. It joined thousands of similar documents, technical analyses of captured Allied equipment that painted consistent pictures of Japanese technological deficiency. These reports would survive the war, captured by American occupation forces and preserved in archives. They provide valuable historical evidence of how Japanese technical specialists assessed their own capabilities compared to opponents. In May 1945, the war in Europe ended with Germany's surrender. American industrial capacity, previously divided between two theaters, now focused entirely on the Pacific. B-29 Superfortress bombers intensified their campaign against Japanese cities. Naval forces tightened the blockade, cutting sea lanes that provided the resources Japan's home islands required. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. On August 6, 1945, an atomic bomb destroyed Hiroshima. On August 9, a second atomic bomb destroyed Nagasaki. On August 15, Emperor Hirohito announced Japan's surrender in a recorded radio broadcast. The war ended. Lieutenant Commander Genda survived. He would play significant roles in post-war Japan, eventually rising to Chief of Staff of Japan's Air Self-Defense Force. His experiences examining and flying captured American aircraft informed his understanding of what modern air forces required. The Japan Air Self-Defense Force he helped build emphasized reliability, maintainability, and integration with American equipment and procedures. The captured Corsair at Kanoya Air Base was likely destroyed in the chaotic final months of the war, either by American air raids or by Japanese forces preventing its recapture. No records confirm its ultimate fate, but the lessons it taught endured. Japanese engineers who examined the Corsair and other American aircraft during the war applied those lessons to rebuilding Japanese industry. The emphasis on quality control, manufacturing precision, and design for production that characterized American wartime industry became hallmarks of post-war Japanese manufacturing. Companies like Toyota, Honda, and Sony built global reputations on reliability and quality that owed much to lessons learned studying American equipment during and after the war. The F4U Corsair continued production until 1952. Total production reached 12,571 aircraft. It served with distinction in the Korean War from 1950 to 1953, primarily in ground attack roles, as jet fighters assumed air superiority missions. Foreign air forces operated Corsairs through the 1960s. The final combat missions by Corsairs occurred in July 1969 during the brief football war between Honduras and El Salvador. On July 17, 1969, Honduran Captain Fernando Soto, flying an F4U-5, shot down 3 Salvadoran aircraft, including 2 Corsairs, the final combat victories for the type. From first flight in 1940 to final combat missions nearly 30 years later, the Corsair proved one of aviation history's most successful and long-lived fighter designs. The story of Japanese examination of the Corsair is ultimately a story about technological awakening. Japan entered the war confident in its aviation capabilities. That confidence was justified initially. Japanese aircraft and pilots dominated early air combat, but confidence blinded leadership to America's potential once its industrial base mobilized. By the time Japanese engineers examined captured Corsairs in detail, understanding the full extent of American technological advantages, the war was already lost. The lessons came too late to affect outcomes. But those lessons shaped the peace that followed. Japanese engineers learned humility from defeat. They learned to respect functional engineering over elegant theory. They learned that quality and quantity need not be mutually exclusive if manufacturing processes are properly designed. These lessons, painful in their acquisition, served Japan well in rebuilding. The economic miracle of the 1950s through 70s owed much to application of principles Japanese engineers had observed in American equipment. The synthesis of Japanese attention to detail, with American emphasis on manufacturing efficiency, created industrial capabilities that made Japan a global economic power. The Corsair that Lieutenant Commander Genda flew in April 1945 represented more than an enemy fighter. It was evidence of what was possible when engineering excellence combined with adequate resources and sophisticated manufacturing. For Japanese aviation specialists who had struggled throughout the war against material shortages and industrial limitations, the Corsair revealed the vast gulf separating their capabilities from American achievements. That 2,000 horsepower R2800 engine was unbeatable, not because Japanese engineers lacked understanding of engine theory. They understood thermodynamics, metallurgy, and mechanical engineering, as well as their American counterparts. The engine was unbeatable because it represented industrial infrastructure Japanese industry could not match. The machine tools, the metallurgical processes, the quality control systems, the supply chains providing consistent high-quality materials, all the infrastructure underlying manufacture of such engines at scale, with consistent reliability. Japan could design comparable engines on paper. The Nakajima Homare theoretically approached the R2800's performance, but Japanese industry could not consistently manufacture those engines to specifications. Quality varied between production batches. Reliability was questionable. Power output often fell short of ratings. These failures stemmed not from design deficiencies but from manufacturing limitations. The Corsair taught Japanese engineers that modern warfare was as much about manufacturing as design. Adequate designs produced in massive quantities with consistent quality defeated superior designs produced in limited numbers with variable quality. This lesson shaped Japanese industrial philosophy for decades. When Japanese engineers acknowledged that the Corsair's 2,000 horsepower engine was unbeatable, they acknowledged more than engine specifications. They acknowledged the industrial system that made such engines possible, the investments in infrastructure, the emphasis on quality control, the sophisticated supply chains, the trained workforce, all the elements of modern industrial production. Japan would rebuild with these lessons in mind. The defeat taught humility. American equipment taught practical engineering. The combination produced industrial capabilities that served peacetime Japan far better than wartime hubris had served military ambitions. The story ends not with triumph, but with acknowledgement and learning.